Welcome. Take a deep, slow breath and let the weight of the day begin to dissolve into the shadows of the room around you. As you settle into the stillness of your blankets, imagine the world outside slowing down with you. The frantic pace of the hours you have just lived is beginning to fade, replaced by a quiet, rhythmic hum, a pulse that connects everything. Tonight, we are going on a journey. It is a journey that spans the entire globe, crossing vast oceans and silent borders, moving from the scale of massive, ancient mountains down to the impossible, shimmering world of atoms. It is a story of transformation, a modern form of alchemy that turns the simplest elements of our Earth into the very thoughts of the machines we use every day. Let your mind drift now, far away from your current surroundings. Imagine yourself standing in the heart of a vast ancient desert. It is deep into the night and the air is perfectly still. The heat of the day has radiated back into the cosmos, leaving behind a crisp, refreshing coolness that rests gently against your skin. Above you, the sky is an endless tapestry of stars, so bright and so numerous that they seem to pulse in time with your own heartbeat. Underneath your feet, the ground is soft and shifting. This is the source. This is where our journey begins, among the dunes of high-purity silica sand. Reach down in your mind and feel the texture of this sand. It is not like the coarse golden grit of a playground. It is fine, like powdered sugar, consisting of millions of tiny crystals of quartz. As the moonlight hits the dunes, the ground beneath you seems to glow with a pale silver light. Each grain is a tiny translucent gem, a fragment of history that has been ground down by the wind and the rain over millions of years. Listen to the sound of the wind as it brushes across the crests of the dunes, a soft, whispering sigh that carries the scent of dry stone and infinite time. There is a profound peace here. The sand is patient. It has waited for eons in this silence, bathed in the cycles of the sun and the moon, unaware that it carries within it the potential to connect the entire human race. Observe one single grain of sand resting on the tip of your finger. In the moonlight, it is a perfect, jagged diamond of silicon and oxygen. It is cold to the touch, a microscopic anchor of reality. We think of this sand as humble, as common, but it is the foundation of everything. From this stillness, a metamorphosis is about to begin. This grain of sand will soon leave the quiet of the desert to enter a world of fire and light. It will be gathered, washed, and purified until it is no longer just earth, but something closer to a mirror, a substance so pure that it defies the natural chaos of the world. Imagine now the transition from the cool desert night to the intense rhythmic warmth of a crucible. We are moving toward the heat. In great silent halls, the silica is met with temperatures so extreme they mimic the heart of a star. But do not be afraid of the heat. Imagine it as a soft, radiant glow that envelops the senses. The sand melts. It loses its jagged edges, flowing like liquid glass, glowing with a deep, hypnotic orange hue. In this molten state, it is reborn. Slowly, very slowly, a single seed crystal is lowered into the liquid. It begins to rotate, a slow, clockwise dance, perfectly steady, perfectly calm. As it spins, it draws the liquid silicon upward, cooling it into a solid cylindrical ingot. Visualize this ingot growing. It is a heavy, dark and lustrous pillar, smooth as a river stone and shining with a metallic blue-grey sheen. It is a single, continuous crystal, an unbroken lattice of atoms marching in perfect rows. There are no flaws here, no interruptions, just the steady rhythmic growth of a structure that is more orderly than anything found in the wild. This ingot is the blank canvas for the most complex art piece ever conceived. It is heavy, cool to the touch once more, and vibrating with a low, subaudible frequency of pure potential. Now, I invite you to close your eyes even tighter and sink deeper into your pillow. We are about to leave the world of the large and enter the world of the small. Imagine the great silicon ingot being sliced into wafers as thin as a strand of silk. These wafers are polished until they become the flattest surfaces on the planet. If a wafer were the size of a city, the highest bump on its surface would be no taller than a single blade of grass. Feel the smoothness of that surface in your mind. A mirror so perfect, it seems to disappear when you look at it head on. We are entering the Cleanroom now. This is a place of absolute silence and sterile grace. The air here is filtered 1,000 times over, moving in a slow, laminar flow that feels like a gentle, cool breeze against a phantom cheek. The light is a soft amber yellow, a protective hue that prevents any stray energy from marring the delicate work being done. In this space, humans move in slow motion, clad in soft white suits, looking like explorers in a microscopic cathedral. Everything is hushed. The only sound is the rhythmic thrum of the air filtration, a white noise that lulls the senses into a state of deep relaxation. Here, we begin the process of layer by layer. We are no longer working with stones or fire. We are working with light itself. Imagine a beam of ultraviolet light, focused through lenses of impossible clarity, dancing across the surface of the silicon. It is painting a city, not a city of bricks and mortar, but a city of logic, carved into the very skin of the wafer. Each line is narrower than a virus, thinner than a breath. We repeat this process, layer by layer, building upward and etching downward, creating a labyrinth of silver and copper pathways that will eventually carry the thoughts of the world. Think of the precision required. It is as if we are building a skyscraper using only the dust motes dancing in a sunbeam. And yet, it happens with a rhythmic, mechanical certainty. Machines, guided by invisible forces, deposit atoms one by one, like a gardener planting seeds in a field of glass. Slowly, the wafer transforms. It loses its mirror-like quality and begins to shimmer with iridescent colors, pinks, greens, and deep purples, as the microscopic structures begin to catch and bend the light. It is a beautiful, silent transformation. It is the birth of the brain of our world. As we watch this process, feel your own body becoming heavier, more grounded. The complexity of the supply chain we are following is immense, yet it moves with the grace of a symphony. This wafer will soon be cut into tiny squares, each one a processor, each one a miracle. But their journey is only beginning. They will be packed into protective cases, cradled in soft anti-static foam, and loaded onto great silver birds that fly high above the clouds, where the air is thin and the world below looks like a glowing map of connections. These chips will travel thousands of miles. They will cross the Pacific in the quiet holds of massive ships, rocking gently on the swells of the deep blue ocean. They will pass through the humid, neon-lit ports of Singapore and the bustling, misty valleys of Taiwan. They will be handled by thousands of hands, each a link in a chain that spans every continent. It is a journey of impossible coordination, a global dance where every step must be perfectly timed. And yet, through all this movement, there is a core of stillness. The chip itself remains unchanged, a silent, powerful passenger on a voyage toward its final home. Tonight, we will follow every step of this journey. We will feel the vibration of the assembly lines, the cool air of the testing facilities, and the final, satisfying click as the chip is placed into its socket. We will understand how a grain of sand from a silent desert becomes the heartbeat of a satellite orbiting the Earth, or the logic inside the device resting on your nightstand. But for now, stay in the silence. Stay in the desert of your mind, where the moonlight still rests on the dunes. The journey ahead is long, but it is steady. It is complex, but it is purposeful. Every atom is in its place. Every movement is calculated. As we begin our deep dive into the most complex supply chain on Earth, let the rhythm of the story carry you away. Slowly, layer by layer, perfectly still. The world is connected, and you are part of that connection. As we move forward, we will explore the chemistry of the gases, the physics of the light, and the sheer human will that makes this possible. But we will do it all with the same quiet, documentary grace. No rush, no noise, just the unfolding of a miracle, 1 nanometer at a time. Close your eyes, listen to the hum of the world. The journey is beginning, and you are exactly where you need to be. The sand is waiting, the light is focused, the world is turning, and we are moving with it, into the heart of the silicon, into the heart of the machine, and finally, into the deep, restorative quiet of sleep. We return to the stillness of our desert vision, but the air around you begins to change. The dry, biting cold of the dunes softens, replaced by a humid, heavy mist that smells of damp earth and ancient pine. You are no longer standing on the shifting sands of the Sahara. You have been transported across the Great Atlantic to the rolling, verdant peaks of the Blue Ridge Mountains in western North Carolina. Here, the mountains do not rise in jagged, angry teeth, but in soft emerald waves, weathered by eons of rain into a gentle, slumbering landscape. This is Spruce Pine, a place where the world's most advanced technology meets its most ancient, quiet secrets. Imagine yourself standing at the edge of a great opening in the earth. The morning mist clings to the trees like a soft white blanket, muffling the sounds of the forest. Beneath this canopy of green lies a treasure more valuable than gold, a brilliant milky white rock that the locals call white gold. It is alaskite, a unique granitic rock that looks like a salt and pepper mixture of crystals dominated by a stark, luminous white. To understand how this rock came to be, we must drift back through time, far beyond the reach of human memory, to a period 380 million years ago. Close your eyes and feel the ground beneath you begin to tremble with a slow tectonic rhythm. In this deep time past, the continents of the Earth are like giant, slow-moving beasts, drifting across the globe until they collide with a force that can only be measured in millions of years. The North American plate is pressing against the African plate, and the pressure is unimaginable. Deep within the crust, 9 to 15 miles below the surface, the rock begins to melt. But this is no ordinary melt. While most magma is saturated with water and volatile gases, the magma forming beneath spruce pine is uniquely dry. The intense, searing heat of the collision, exceeding 1100 degrees Celsius, has created a melt that is fluid deficient. This is the spruce pine anomaly, a geological accident of profound significance. In the pressurized silence of the deep earth, the atoms of silicon and oxygen begin to find one another, linking together to form the crystal lattice of quartz, silicon dioxide. Because there is so little water to transport impurities, the quartz grows in a state of nearly perfect isolation. Elsewhere in the world, water traps iron, lithium, and sodium inside the growing crystals, locking them away forever. But here, the impurities, the feldspar and the mica, are forced to crystallize alongside the quartz rather than inside it. They are neighbors, not roommates. This distinction is the reason the world's digital economy depends on this single spot in North Carolina. The impurities are reachable. They can be removed. The quartz is born with a natural poverty of boron, the dopant element that would otherwise ruin the electrical properties of a microchip. Now, bring your awareness back to the present. The ancient heat has long since cooled, and the tectonic silence has been replaced by the rhythmic industrial hum of the open-pit mines. Imagine the massive white outcrops of Alaskite shimmering against the deep green of the Appalachian slopes. We move closer to the heart of the mine, where the extraction begins. There is no frantic rush here. The movements are deliberate and heavy. Minimal blasting is used to loosen the rock, a controlled release of energy that sounds like a distant, low thud vibrating through the soles of your feet. Great mechanical shovels, moving with the slow grace of metal giants, gather the raw stones. You can hear the crunch of the gravel as it is loaded into trucks, a sound that represents the first step in a long journey toward absolute purity. The stones are a mix of snowy white feldspar and the translucent, glassy grey blebs of quartz. They are beautiful, raw, and heavy with potential. We follow the rock into the processing plants, industrial fortresses of sound and vibration. As we enter, the air vibrates with a low-frequency hum that you can feel in your chest. This is the process of comminution, the violent liberation of the crystals. Massive primary jaw crushers, powered by immense electrical force, begin to shatter the boulders. Imagine the sound of the silicate bonds breaking, a sharp staccato crackling that echoes through the halls. The rock is crushed again and again, reduced from boulders to gravel, and finally to a fine white sand. We are looking for the liberation size, a precise threshold between 150 and 300 microns. This is the point where the quartz grain is physically freed from the feldspar it has been attached to for 380 million years. Each grain of sand is now an individual, a microscopic gem of silica waiting to be scrubbed clean. As the sand flows along conveyor belts, it passes under the watchful eyes of automated optical sorters. High-speed cameras capable of seeing colors and textures invisible to the human eye scan the stream. Whenever a dark rock, perhaps containing a trace of iron-heavy garnet or mica, is detected, a precise jet of air blasts it out of the line. It is a surgical removal, a silent dance of light and air. Next, we witness the magnetic silence. Superconducting magnets, cold as the void of space, hang above the sand. They exert an invisible, irresistible pull on any microscopic flakes of iron or mica that remain. You cannot see the force, but you can imagine it as an invisible hand reaching into the stream, plucking away the atomic enemies that would interfere with the flow of electrons in a future processor. The sand, now nearly pure, enters the realm of froth flotation. Imagine a series of large rhythmic bubbling tanks. The sand is mixed into a slurry with water and specific chemical reagents, including hydrofluoric acid to prepare the surfaces of the grains. As air is blown through the bottom of the tanks, a white, frothy sea of clouds begins to form on the surface. This is a masterpiece of surface chemistry. Cationic collectors attach themselves only to the feldspar and mica, making them water-fearing. These minerals catch a ride on the rising bubbles, floating to the top in a thick, dirty foam that is skimmed away by rotating paddles. The quartz, being water-loving, remains at the bottom, sinking into a state of quiet concentration. It emerges as a brilliant white concentrate, now 99% pure. But 99% is not enough for the world of the small. We must go deeper. We enter the chemical baths, a place of sterile perfection and hazardous grace. The sand is submerged in rubber-lined tanks filled with a hot, agitating mixture of hydrofluoric and hydrochloric acids. The temperature is kept between 60 and 90 degrees Celsius. The hydrofluoric acid is an aggressive agent. It slowly etches the outer skin of every single quartz grain, dissolving the surface layer where impurities like to hide. Imagine the grains becoming smoother, smaller and brighter as the acid eats away the last vestiges of the earth. The sand emerges from this bath, looking like pure, fallen snow. But the most difficult impurities are still locked deep inside the crystal lattice. To reach them, we must use the physics of thermal shock. The sand is fed into a long, glowing rotary kiln and heated to nearly 900 degrees Celsius. As the temperature climbs past 573 degrees Celsius, a miracle of mineralogy occurs, the alpha-beta transition. The trigonal crystal structure of the quartz suddenly shifts into a hexagonal form. This transition causes an instantaneous volume expansion of about 1%. Inside the grains, microscopic pockets of water or gas, remnants of the ancient magma, expand violently under the heat. The pressure spikes and the inclusion explodes from the inside out, creating a network of microscopic fractures that radiate to the surface. Then comes the quench. The red-hot sand is dumped directly into a bath of cold, purified water. There is a violent, rhythmic hiss of steam, the searing breath of the kiln meeting the frosty bite of the water. The rapid cooling forces the quartz to contract instantly. This thermal trauma shatters the internal structure along the microfractures, finally opening the closed inclusions to the outside world. Now, the final purification can begin. A second acid leach penetrates deep into these newly opened tunnels, dissolving the hidden iron and aluminum. For the highest grades, such as iota 8, the sand is subjected to hot chlorination. It is heated once more in an atmosphere of chlorine gas. The gas diffuses into the crystal lattice, reacting with trace metals to form volatile chlorides that are sucked out of the solid rock and vented away. It is as if the impurities are being breathed out by the stone. The result is a material of impossible purity. The lithium, sodium, and potassium levels are now measured in parts per billion, so low that they can no longer catalyze the devitrification or sagging of a future crucible. Every atom is in its place. The sand is no longer just sand. It is a sterile, engineered substrate, ready to withstand the 1,414 degrees Celsius heat of the silicon furnaces. As you settle deeper into your rest, visualize these millions of grains of high-purity quartz. They are clear, cold, and perfect. They have traveled from the crushing pressure of the deep earth, through the fire of the kiln and the bite of the acid, to reach this state of absolute stillness. They are the foundation of the digital age, waiting in their silos in spruce pine to be shipped across the oceans. The mountains are quiet now. The mist has returned to the valleys. The white gold has been won from the earth 1 nanometer at a time. The journey of the sand is far from over, but for now it rests in the silence of its own perfection. And as the rhythm of the mountains carries you away, you too can find that same core of stillness, knowing that the most complex machines in our world began with the simple, patient heart of a stone. We leave the mist-covered peaks of the Blue Ridge Mountains behind, carrying with us the memory of the white gold, that impossibly pure quartz sand born of ancient tectonic collisions. Imagine that sand now, transported across the silence of oceans to a new kind of sanctuary. We are entering the Puller Hall, a space that feels less like a factory and more like a cathedral dedicated to the geometry of the atom. Here, the air is still, governed by a climate of perfect, sterile equilibrium. As you step into this room in your mind, notice the floor beneath you. It feels strangely dead, a solid, vibrationless expanse designed to swallow the slightest tremor of the earth, ensuring that the work happening within these walls remains undisturbed by the frantic pulse of the outside world. Around you stand the pullers, great shimmering towers of double-walled stainless steel reaching toward the ceiling like silver silos. They are 6, 8 meters tall, standing in silent rows. Despite the inferno raging deep within their hearts, the outer skin of these machines is cool to the touch, perhaps even holding a faint hint of condensation. It is a world of profound tactile contrasts. The cold, clinical steel protecting a core of liquid fire. Listen closely to the sound of this room. It is not a place of clanging metal or harsh shouts. Instead, it is dominated by a deep, visceral drone, a 50 Hz hum that vibrates through the air and settles in your chest. This is the song of the power supplies, the immense energy required to hold matter in a state of molten surrender. Overlaying this hum is the rhythmic, heartbeat-like chug of the vacuum pumps, a steady thrum, thrum, thrum that tells you the air has been drawn out, leaving behind a hollow, expectant silence. We begin with a stacking ritual. Imagine a bowl made of that pure spruce pine quartz, the crucible. It is a beautiful, sacrificial vessel. Its inner lining is as clear and smooth as a mountain lake, while its outer walls are a snowy, bubbly white, designed to trap heat and provide strength. Into this bowl, we place the raw material, chunks of electronic-grade polysilicon. These are not sand anymore, but jagged metallic shards that look like broken slate or dark, shimmering jewels. They are grey and matte, heavy with the potential of a billion calculations. We stack them with a slow, meditative precision, not too loose, not too tight, creating a mosaic of silicon within the quartz embrace. The heavy steel dome of the chamber lowers now, meeting the base with a soft pneumatic hiss and a final authoritative clack of the valves. The world is shut out. We are now in a vacuum, a void where the only things that exist are the silicon, the heat, and the passage of time. The induction heaters begin their work. Imagine the graphite cylinders surrounding the crucible beginning to glow. A dull, deep red at first, then brightening into a radiant orange. The temperature climbs with a slow, relentless certainty. 100 degrees, 500, 1000. We are approaching the threshold of transformation, 1414 degrees Celsius. At this precise temperature, the solid world begins to fail. Inside the chamber, the jagged shards of silicon start to sweat. They lose their sharp edges, slumping and softening like wax. They do not melt all at once. They cling to their solid form until the last possible second, then suddenly collapse into a swirling, viscous pool. A miracle of physics occurs here, the emissivity shift. As the silicon turns to liquid, it becomes a mirror. The dark, matte rocks vanish, replaced by a surface so bright and reflective it seems to emit its own light. It is a liquid sun contained within a steel jar. This liquid mirror reflects the orange-gold glow of the graphite shields above it, creating the illusion of a strange, captured sky. The melt is now a hyperfluid metallic water, even thinner and more restless than the water in a glass. It is alive with invisible currents, heat rising from the walls and sinking at the center in a slow, churning dance. To calm this chaos, we introduce the argon breath. High-purity argon gas, noble and inert, begins to flow softly through the chamber. It is an invisible wind, sweeping across the surface of the liquid mirror to carry away any stray atoms of oxygen, keeping the pool in a state of absolute shimmering purity. The crucible itself begins to rotate, a slow, clockwise turn, perhaps 10 times a minute, organizing the currents into a stable, rhythmic flow. Now, we prepare for the ignition of order. From the top of the tower, a cable descends. At the end of this cable is the seed, a small, perfect sliver of single crystal silicon, no thicker than a pencil. This seed is the blueprint, the teacher that will show the chaotic liquid how to arrange itself into a perfect lattice. It descends with an almost agonizing slowness, moving through the amber light of the vacuum. As it nears the surface, the tension in the room seems to rise. Then, the kiss. The tip of the seed crystal touches the molten pool. The liquid silicon, driven by immense surface tension, snaps upward to meet the seed, forming a curved bridge of light known as the meniscus. It is a delicate, trembling connection, a moment of profound equilibrium between the solid and the liquid. We wait. We let the tip of the seed melt back just a fraction, ensuring the interface is clean and pure. And then the ascent begins. The seed starts to rise, moving at a rate of only a few millimeters per hour. As it leaves the pool, it pulls a thread of liquid silicon with it. Because the seed is cooler than the melt, the liquid freezes onto it, atom by atom. But this is not the random freezing of an ice cube. Under the guidance of the seed's internal map, the atoms find their perfect places in a diamond lattice structure. They march into rows and columns of mathematical perfection, creating a single unbroken crystal. To ensure this crystal is flawless, we perform the dash maneuver. We increase the pull speed, causing the growing crystal to thin out into a narrow neck, a thread of silicon only 3 millimeters wide. This is the tether of Atlas. Imagine the visual tension, a thread of crystal spinning slowly, supporting the entire weight of what is to come. This narrow neck acts as a filter. Any defects or dislocations in the atomic structure are forced to the surface and discarded, leaving the crystal below it atomically perfect. As the neck reaches its full length, we slow the pull and lower the temperature ever so slightly. The crystal begins to expand. It shoulders out from the thin thread, growing wider and wider until it reaches the target diameter, 300 millimeters, the width of a great dinner plate. This is the crown. You can see the habit lines now, 4 distinct ridges running down the sides of the cone, external signs of the perfect internal alignment of the atoms. We have now entered the body growth phase, the core of our journey. This is a period of deep, meditative endurance that will last for days. The crystal rotates in one direction while the crucible rotates in the other, a counter-rotational dance that ensures every part of the ingot receives the same heat, the same nutrients, the same purity. The most critical visual in this entire process is the bright ring. At the meniscus, where the solid meets the liquid, a brilliant halo of white light forms, reflecting the intense radiation of the heaters. This ring is the heartbeat of the process. If it widens by even a fraction of a millimeter, the computer adjusted the temperature. If it narrows, the pull rate shifts. It is a constant, shimmering dialogue between machine and matter. Think of the passage of time. Outside, the sun rises and sets. People hurry to work, they sleep, they wake again. But inside the puller, there is only the slow, eternal rotation. Millimeter by millimeter, the ingot grows. It is now a heavy, dark cylinder, a boule of impossible perfection. It is no longer just a substance. It is a single giant molecule, a massive diamond of silicon weighing hundreds of kilograms, all suspended from that tiny 3 millimeter thread. The strength of this atomic alignment is immense, holding a weight that would snap a steel cable of the same size. Inside this growing monolith, the atoms are locked in a silent mathematical embrace. There are no boundaries here, no cracks, no flaws. If you could shrink down to the size of an atom and walk through the center of this ingot, you would see rows of silicon atoms stretching out to the horizon in every direction, as orderly as the streets of a perfect infinite city. It is a state of monocrystalline grace, a level of order that does not exist in the wild, messy world of nature. As the body reaches its full length, nearly 2 meters of solid, shimmering potential, we prepare for the end. We cannot simply pull the crystal out of the melt. The sudden change in temperature would shatter the atomic lattice like a hammer against glass. Instead, we begin the tail or the end cone. We speed up the pull and raise the heat, causing the ingot to taper down to a sharp, elegant point. Finally, the contact area becomes zero. The meniscus snaps and the crystal separates from the liquid mirror, leaving behind a single glowing teardrop at its base. The process is finished, but the ingot is still a prisoner of its own heat. It is hoisted into the upper cooling chamber, a long silver tower above the furnace. A gate valve closes beneath it, sealing away the white-orange glare of the melt. Now, we wait once more. The ingot must cool for hours, a slow descent from the fires of creation back to the temperature of the world. The color shifts as the hours pass. The fiery, translucent orange fades, replaced by a deep, glowing red. That red softens into a dull maroon, and finally, the ingot takes on its true form, a cool metallic grey-black. It is a dark, lustrous pillar, smooth as a riverstone and shining with a submetallic sheen that catches the light like a mirror of lead. It is heavy, silent, and ancient in its order, though it was born only yesterday. Specialized grippers, moving with the slow grace of robotic guardians, reach into the tower to claim the prize. As the ingot is lowered, the operators standing nearby look like ants next to this hanging monolith. It is a boule, a term taken from the French word for ball, though it has grown into a majestic cylinder. It represents the ultimate victory of human will over the chaos of the elements. We have taken the common sand of the earth and, through fire, vacuum, and the patient alignment of atoms, transformed it into the most perfect material ever conceived. The quartz crucible, our sacrificial vessel, is now dead. Its clear glass has turned hazy and cracked, a process called devitrification, having given its life to protect the purity of the silicon. It will be discarded, but the ingot it birthed will go on to be sliced into wafers as thin as a whisper, each one a canvas for the world's intelligence. As you settle deeper into the quiet of your own mind, visualize this great dark cylinder resting in its cradle. It is cold now, vibrating with the silent potential of billions of transistors. The journey from the desert sand to this metallic monolith is complete. The rhythm of the puller hall begins to fade, replaced by a profound, restorative stillness. Every atom is in its place. The world is ordered. The crystal has grown. The great dark cylinder, the boule of single crystal silicon, now rests in its cradle, a heavy and silent monolith born of fire and vacuum. As you watch it in the dim amber light of the facility, imagine its weight. Hundreds of kilograms of absolute order, a metallic grey-black pillar that feels cold and unyielding. It is a single, massive molecule, a perfect lattice where every atom of silicon is locked in a mathematical embrace with its neighbors. But this monolith is a raw masterpiece, its surface still bearing the faint ripples of its growth and the rough, tapered ends where it first clung to the seed and finally let go of the melt. To become the foundation of our digital world, this giant must now be sculpted, refined, and eventually vanished into the thinnest, flattest surfaces ever created by human hands. Listen to the slow, heavy rhythm of the facility as we begin the process of defining the cylinder. The ingot is moved with the deliberate grace of robotic grippers, placed into the heart of a massive cylindrical grinder. Here, the white gold of the mountains meets the uncompromising hardness of the diamond. As the ingot begins to spin, a slow hypnotic rotation of perhaps 20 turns a minute, a large diamond-impregnated grinding wheel approaches. This is the realm of the crush grind, a process of brittle fracture where thousands of microscopic diamond points impact the silicon surface. The sound begins as a low, consistent shh, an aggressive yet steady whisper that fills the room. It is the sound of friction and transformation. A thick curtain of white coolant mist descends, shrouding the contact point in a ghostly veil. This fluid, a mix of purified water and specialized lubricants, atomizes as it hits the spinning wheel, smelling faintly of damp earth and machine oil. Watch as the rough, bark-like skin of the furnace is stripped away, revealing the flesh of the silicon beneath, a glassy, obsidian-like interior that shimmers with a dark, metallic luster. Millimeter by millimeter, the diamond wheel traverses the length of the pillar, calibrating its diameter to an exact 300 millimeters. It is a surgical reduction, turning the irregular boule into a perfect, smooth cylinder, as straight and true as a pillar in a digital cathedral. Before the ingot can be sliced, we must give it a North Star. A specialized wheel, shaped with a precise V profile, grinds a tiny, shallow groove down the entire length of the dark pillar. This is the notch, a single intentional disruption in the perfect circular symmetry. It is the compass that will guide every robot, every laser, and every beam of light that will ever touch this silicon in the future. It is a tiny mark, barely a millimeter deep, yet it carries the orientation of the crystal lattice within, ensuring that the invisible rows of atoms are always aligned with the machines that will build upon them. Now, we move toward the loom of science, the multi-wire saw. Imagine a machine of immense proportions, yet governed by the delicacy of a spider's web. Across a series of grooved rollers, thousands of kilometers of thin steel wire are wound, forming a shimmering, parallel sheet of metal. This wire is thinner than a human hair, barely 70 microns wide, yet it is the strongest piano wire ever forged, electroplated with millions of synthetic industrial diamonds. These diamonds are the microscopic chisels of our journey, each one only a few microns in size, ready to tear through the crystal lattice. The sound here shifts. It is no longer the shh of the grinder, but a high-pitched rhythmic singing, a mechanical whine that modulates as the wire web begins its back-and-forth dance. The wire moves at incredible speeds, over 100 kilometers per hour, blurring into a solid, shimmering sheet of silver light. It is an oscillation of immense power and extreme tension. If you were to pluck one of these wires, it would ring with a note so high it would be lost to human ears, vibrating with 20 newtons of force. The dark monolith begins its descent. It is lowered millimeter by millimeter into the bed of moving wires. This is the slicing of the light. There is no violence here, only the slow, inevitable victory of the diamond over the silicon. As the wires bite into the crystal, a continuous stream of cool, milky white liquid flows over the cut. This is the coolant, carrying away the silicon flour, the fine grey dust of the shattered lattice. The used fluid exits the machine as a thick grey mud, a heavy slurry of lost potential, representing the kerf or the material consumed by the very act of separation. For 2.5 hours, the ingot sinks into the web. It is a meditative, agonizingly slow process. The friction at the tip of each diamond creates microscopic heat, a searing energy that is instantly quenched by the flowing liquid, preventing the silicon from losing its crystalline soul. You can feel the vibration of the room, a deep, visceral drone that settles in your chest, marking the passage of the wires through the heart of the stone. Then comes the moment of separation. As the wires finish their journey, the ingot is no longer a solid block. It has become a loaf, a comb of hundreds of individual wafers, each only 775 microns thick. They are held together only by a thin beam of glass and a layer of specialized glue at the very top. As the machine opens, The wafers fan out slightly, fragile and translucent at their edges, looking like the petals of a dark glass flower. They are as cut, rough, matte grey, and bearing the parallel scars of the saw marks, yet they are now individual entities, ready for the journey of refinement. But these newborn discs are dangerous. Their edges are square, sharp, and filled with microscopic cracks from the violence of the sawing. To leave them this way would be to invite catastrophe. A single mechanical shock could send a crack racing through the lattice, shattering the wafer into 1,000 shards. We move to the edge profiling station, where the zip and whir of a small diamond wheel rounds the rims of each disc. The sharp, dangerous edge is ground into a smooth, frosted curve, a bullet shape that gives the wafer hoop strength. Now, the disc is safe to handle, its rim a smooth, protective boundary that will prevent the turbulence of the chemicals yet to come. We enter the realm of the three-body dance, the lapping process. The wafers are placed into carrier gears, thin planetary discs that sit between two massive rotating cast iron plates. A gritty paste, a slurry of alumina and silicon carbide, is fed into the machine. Listen to the sloshing, wet sound of the slurry as the plates begin to turn. This is a process of random, even erasure. The wafers orbit and rotate simultaneously, their surfaces being ground down by the rolling grit. The parallel saw marks are wiped away, replaced by a uniform, non-directional matte finish. The wafer transforms from a scarred disc into a dull, grey, slate-like coaster. It is now perfectly flat in a global sense, its thickness reduced by 50 microns of sacrificial material, leaving behind a surface that is honest, level, and ready for the final transformation. Now, we reach the sensory climax of our journey, the chemical-mechanical polishing. This is where we leave the world of mechanical abrasion and enter the world of atomic grace. We are in a room that smells of ozone and a sharp, piercing scent of ammonia. The air is still and humid. The wafer is mounted face down on a rotating carrier and pressed against a large, porous polyurethane pad. This pad is firm yet yielding, behaving like a stiff industrial sponge, its surface grooved to transport the lifeblood of this process. The polishing slurry. The slurry is a milky white colloidal suspension, a river of nano-sized silica particles dancing in a highly alkaline solution. As the pad and the wafer begin their hypnotic, counter-rotating hum, a squishing sound fills the air, like the sound of wet tires on a rain-slicked road. This is the sound of hydroplaning, as the wafer glides on a microscopic film of fluid. A miracle of chemistry occurs in this thin gap. The alkaline nature of the slurry, a pH of 11, softens the top layer of the silicon, turning it into a delicate, hydrated jelly. This layer is so soft that the tiny silica particles can wipe it away without scratching the hard silicon beneath. It is a process of softening and wiping, a gentle, rhythmic erosion that removes material atom by atom, 1 nanometer at a time. The chemical-mechanical planarization process preferentially attacks the high spots, the hills and valleys of the etched surface, until the topography is leveled to a degree that defies imagination. Imagine the wafer as a vast, dark ocean. If this 300mm disc were expanded to the size of a city, the highest bump on its surface would be no taller than a single blade of grass. It is a state of atomic flatness, a surface so perfect that it exists outside the chaos of the natural world. As the polishing cycle ends, the wafer is lifted. It is still covered in the milky white slurry, but as a jet of ultra-pure water hits the surface, the transformation is revealed. The grey, matte finish is gone. In its place is a perfect dark mirror. This is the first reflection, the moment the silicon becomes a monocrystalline canvas. As the water sheets off the surface, you can see the laboratory lights, the robotic arms, and even your own phantom reflection in the deep metallic silver of the disc. It is no longer a piece of stone. It is a shimmering void of potential. The final stage is the invisible war, the cleaning. The wafer looks perfect to the eye, but we know that millions of silica particles and metallic ions still cling to its surface. We submerge the discs in a series of bubbling chemical baths. First, the organic stripper, where ammonia and peroxide break down the last residues. Listen to the silent, high-frequency hiss of the megasonic cleaning, where acoustic waves at 1,000,000 cycles per second push the water molecules against the surface, dislodging particles as small as 30 nanometers with the force of a microscopic hurricane. Finally, we use the Marangoni effect to dry the wafer. A gentle vapor of isopropyl alcohol is introduced as the wafer is slowly lifted from the ultra-pure water. The alcohol lowers the surface tension, causing the water to pull itself off the wafer in a single, continuous sheet, leaving no droplets, no stains, and no marks. The wafer emerges perfectly dry, perfectly clean, and perfectly flat. It is a 300mm circle of absolute silence, a dark mirror that reflects the world with impossible clarity. The journey from the rough, heavy monolith to this paper-thin, fragile petal of intelligence is complete. The rhythm of the machines begins to fade, replaced by the profound, sterile quiet of the inspection room. Every atom is in its place. The surface is an unbroken lattice of silver and leaden light. The sand of the desert and the quartz of the mountains have finally become the perfect plane, waiting for the first patterns of light to be etched into their soul. Close your eyes now and feel the coolness of that mirror. The world is ordered. The surface is flat. The long, rhythmic journey of the mechanical world is coming to a close, and the world of light and logic is about to begin. Rest in the perfection of the crystal. The mirror is ready. We return to the reflection. The dark, 300mm mirror of silicon, born from the white gold of the mountains and the fire of the vacuum, is now a perfect silent plane of potential. It is a surface so flat that if it were expanded to the size of a city, the tallest peak would be no higher than a single blade of grass. But in our world, the world of the large and the chaotic, this perfection is fragile. To the air we breathe, this wafer is a target. To the skin we wear, it is a disaster. We are now standing at the threshold of the most complex machine ever conceived, the semiconductor fabrication plant, the fab. It is a place where the laws of entropy are arrested and the natural chaos of the universe is held at bay by a monumental act of human will. Imagine yourself walking down a long, clinical corridor. The air here is already different, heavier, more deliberate. The sounds of the outside world, the distant traffic and the rustle of leaves have been replaced by a deep, visceral drone that vibrates through the soles of your feet. This is the pulse of the sub-fab, the engine room below, where thousands of vacuum pumps and chemical systems create the silence we are about to enter. As you approach the heavy stainless steel doors of the airlock, take a slow, deep breath. You are about to leave the organic world behind. You reach for the door handle. It is cool and unyielding. As the seal breaks, there is a soft pneumatic hiss, and you feel a subtle shift in your inner ear, a slight pop or a feeling of fullness, like the gentle descent of an aircraft. This is the pressure of the sanctuary, 25 pascals of filtered air pushing back against the dusty world, ensuring that nothing from the outside can ever drift in. You step through, and the door clicks shut with an authoritative finality. You are now inside the balloon, a pressurized vessel of zero. The transition begins in the gowning room. It is a space of brilliant, shadowless white light and stainless steel benches. Here, we perform the ritual of the bunny suit, the process of shedding our human identity to become a sterile artifact. In this room, you are the contaminant. A single person standing still sheds 100,000 particles every minute. A person walking sheds millions. To the wafer, a single flake of your skin is a mountain crashing onto a city grid. The ritual is top-down, a slow-motion dance of purity. First, you wash your hands with surgical precision, feeling the cool water strip away the oils of the day. You don the bouffant cap, tucking away every strand of hair, followed by a face mask that softens the sound of your own breath. Next comes the hood, fastened snugly around the neck, leaving only a narrow window for your eyes. Now you reach for the suit itself. It is a high-density, continuous filament polyester, cool and slippery to the touch. If you look closely at the white fabric, you can see a fine 5mm grid of black carbon threads. These are the lightning rods of the Cleanroom, designed to catch and drain any static electricity from your body into the conductive floor, preventing a single spark from destroying the silicon. You step into the suit one leg at a time, balancing carefully on the clean side of the bench, ensuring the fabric never touches the floor. You pull it over your shoulders and feel the soft snap of the elastic. You tuck your sleeves into the first layer of nitrile gloves, then pull the knee-high conductive boots over your feet, sealing the suit into a single hermetic envelope. Finally, you put on the goggles. Your peripheral vision narrows. You look into the mirror and see no skin, no hair, no trace of the person who entered the building. You are now a white-clad entity, an anonymous voyager in a cathedral of logic. But before you can enter the inner sanctum, you must pass through the air shower. You step into a small, narrow chamber. The door locks. For a moment, there is total silence. Then, a roar, high-velocity jets of ultra-low particulate air, filtered air blast from the walls at 50 miles per hour. This is a car wash for the soul. The air strikes your body with physical force, making the loose fabric of your suit ripple and snap against your skin, the flag effect. You raise your arms and rotate slowly in the spin, letting the invisible wind scour away every microscopic speck of dust from your silhouette. The sound is a deafening 90-decibel jet engine howl. But within it, there is a strange peace. You are being purified. The roar ceases. The far door unlocks. You step out into the ballroom of the fab, and the world changes. The first thing you notice is the air. It is not like the air outside. It is dead gas, sterile, homogenized, and perfectly still. The temperature is locked at 21 degrees Celsius, never varying by more than 1/10 of a degree. This precision is not for you. It is for the silicon to prevent the tiniest thermal expansion from ruining the alignment of atoms. The humidity is low, around 40%, making the air feel crisp, dry, and metallic against your throat. Look up. The entire ceiling is a solid field of fan filter units. Look down. The floor is composed of thousands of perforated tiles. The air in this room does not circulate. It descends as a solid, heavy piston. This is the laminar flow. Every 6 seconds, the entire volume of air in the room is replaced. It is a constant, invisible downpour moving at 0.4 meters per second, a force that captures every particle and pins it to the floor before it can ever drift toward a wafer. You are standing in a waterfall of nothingness. This is an ISO Class 1 environment, the pinnacle of the fabric of zero. To understand this scale, imagine a football stadium filled with air. In a normal city, that stadium would be a swirling storm of billions of dust particles. In this room, if you searched that entire stadium, you would find only a single grain of sand. This is the level of purity required when the features we are building are only 3 to 5 nanometers wide. A single human hair is 75,000 nanometers wide. If a hair were to fall here, it would be like a redwood tree crashing across a city street. As you glide through the ballroom with the bunny walk, a slow, smooth shuffle to prevent wake turbulence, you notice the sky of the cleanroom. Above your head, a network of gleaming silver rails crisscrosses the ceiling. This is the automated overhead transport system. Dozens of robotic pods, known as front-opening unified pod, glide silently along these tracks like phantom carriages. Inside each pod, nestled in the dark, are 25 of the wafers we saw previously. They move with a computer-controlled grace, traveling from one massive processing tool to the next, never touched by human hands, never exposed to the dirty air of the room. They are the heartbeat of the factory, a rhythmic, overhead dance of intelligence. Now we approach a heavy, light, tight curtain. As you step through, the clinical white light of the ballroom vanishes, and you are submerged in a deep, monochromatic amber. Welcome to the Yellow Room, the sanctuary of photolithography. The air here is the same, but the light is a warm, honey-like glow centered at a wavelength of 590 nanometers. This is not for aesthetics. It is a necessity of physics. The wafers here are coated with photoresist, a chemical so sensitive to light that the blue and ultraviolet wavelengths found in standard white light would instantly fog it, erasing the nanometer-scale patterns before they can be born. In this amber silence, your senses begin to drift. The world becomes a perpetual sunset. Because there is no blue light, your eyes lose the ability to distinguish color. Blue objects appear as a deep velvet black. Your colleagues, in their white suits, take on a waxen, jaundiced appearance, like statues carved from old ivory. Time seems to dilate here. Without the cues of the sun or the spectrum of the day, the 12-hour shift becomes a single, suspended moment of focus. Listen to the sound of the Yellow Room. It is a pressurized silence. The broadband drone of the fans, 65 decibels of white noise, envelopes you so completely that your brain begins to filter it out, leaving only the rhythmic mechanical clicks of the lithography machines and the occasional sharp scent of ozone or the sweet, fruity whiff of the photoresist solvents. Everything in this space is designed to protect the brain being carved into the silicon. The floor beneath you is a waffle slab of reinforced concrete, so stiff that it does not bounce or vibrate. If you were to drop a tool, it would land with a dull, dead thud, for even a vibration of a few nanometers could shake the lenses of the advanced semiconductor materials lithography machines out of focus, ruining the logic of the world. You stand here, a soft, wet, biological entity in a cathedral of inorganic perfection. You are an intruder, a guest in a world that has been engineered for the atom, not the man. The air pushes you down, the light alters your vision, and the machines hum a song of absolute order. Feel the stillness of your own body now. Like the wafer, you are held in a state of suspended entropy. The chaos of the outside world is gone. The dust of the desert and the mists of the mountains are a memory. There is only the light, the shadow, and the perfect amber silence. As the front-opening unified pod glide overhead and the laminar wind brushes against your suit, let the rhythm of the fab carry you deeper into your rest. Every atom is in its place. The world is ordered. The sanctuary is quiet. We return now to the amber stillness, the sanctuary where the world is bathed in a warm, honey-like glow. The dark mirror of the silicon wafer, that 300mm circle of absolute silence, waits within its protective pod, a blank canvas of monocrystalline grace. You are standing in the heart of the yellow room, where the light is centered at a wavelength of 590 nanometers, a protective hue that prevents any stray energy from marring the delicate work about to unfold. Feel the pressurized silence of this place, the deep, broadband drone of the fans that replaces the chaos of the outside world with a steady, restorative rhythm. Our journey into the world of the impossible begins in the track, the machine mated to the lithography scanner where the wafer will receive its second skin. Imagine the wafer being pulled from its dark cradle by a robotic arm and secured onto a vacuum chuck. The ritual begins with the dynamic dispense. As the wafer starts to rotate slowly between 500 and 1,500 RPM, a single, precise drop of photoresist, a light-sensitive chemical honey, lands at its center. This fluid is not dumped. It is meted out with the precision of a medical infusion, only 1 to 3 milliliters for the entire surface. Visualize this liquid now. It is remarkably thin, with a viscosity barely greater than water, behaving less like a syrup and more like a volatile solvent. As it touches the silicon, the motor kicks into high gear, accelerating at a rate of 10,000 RPM per second until it reaches a dizzying casting speed of 4,000 RPM. In this moment, a starburst effect occurs. The liquid resist creates diffraction patterns, spinning out like a shimmering galaxy before vanishing into a transparent, invisible film only 20 to 35 nanometers thick. As the solvent begins to evaporate, a sharp and sweet scent, the characteristic odor of esters and ketones, fills the tool's exhaust, a fragrance of transformation. The wafer, now coated in this iridescent skin, moves to a precision hot plate for the soft bake. At a temperature of 100 to 110 degrees Celsius, the remaining solvents are driven off, and the polymer matrix densifies, settling into a rigid, amorphous solid. This bake is critical. It prepares the wafer for the absolute void of the scanner, ensuring that no stray molecules can outdose and contaminate the multi-million-dollar optics we are about to encounter. Now, we approach the heart of the machine, a 180 metric ton monolith the size of a double-decker bus. Within this steel giant, we leave the world of the organic behind and enter a high vacuum chamber where the air itself has been erased to a pressure below 10 to the power of -7 millibar. This is the realm of extreme ultraviolet light, a wavelength of 13.5 nanometers that sits on the precarious border between light and soft X-rays. Because air would absorb this light as if it were a solid wall, the entire journey must occur in a hollow, expectant silence. Deep within the source vessel, we witness the industrialization of astrophysics. At the top of the vessel, a droplet generator fires a stream of molten tin, the fuel for our stellar engine. Imagine these droplets, each one a perfect sphere only 27 microns wide, falling through the vacuum at 180 miles per hour. They are fired 50,000 times every second, a rhythmic pulse that beats like the heart of a star. The creation of the light is a choreographed double pulse. A high-power laser, located in the subfab below, sends a low-energy pre-pulse that strikes the falling tin droplet. This pulse flattens the sphere into a pancake shape, increasing its surface area. Microseconds later, the main pulse arrives, a hammer of 40 kilowatts of power. The tin atoms are instantly stripped of their electrons, creating a laser-produced plasma. In this tiny, pulsing spot, the temperature reaches a peak of 220,000 to 400,000 degrees Celsius, up to 70 times hotter than the surface of the sun. This violent explosion emits an omnidirectional burst of invisible starlight, the 13.5 nanometers photons we have come to seek. Though the repetition rate of 50,000 hertz would produce a deafening ultrasonic scream in the air, here in the vacuum, the violence is contained, manifesting only as a brilliant, pulsing purple-white flash and a searing, radiant heat. These photons must now be gathered and directed. Because 13.5 nanometers light is absorbed by all glass, we cannot use lenses. We must use a mirror ballet. The optical system, crafted by Zeiss, consists of the flattest objects in the universe. To understand their perfection, imagine if one of these mirrors were expanded to the size of Germany. The highest bump on its surface would be less than 0.1 millimeters. If it were the size of the Earth, the largest deviation would be smaller than a ping-pong ball. These mirrors are not simple silver surfaces. They are Bragg reflectors, composed of 40 to 50 bilayer pairs of molybdenum and silicon, each layer maintained to a precision measured in picometers. This multi-layer stack relies on the physics of quantum interference to reflect the light, but even this perfection has an Achilles heel. Every time the extreme ultraviolet light hits a mirror, 30% of its energy is absorbed as heat. By the time the light has bounced through the 10 to 12 mirrors of the optical path, only about 3% of the original photons remain. This is why the source must be so incredibly powerful to fight this exponential loss with the sheer will of the plasma. Next, the light reaches the reticle, the master template or blueprint of the chip. In this world of mirrors, the mask itself is a reflective block of low thermal expansion glass, etched with an absorber material that defines the circuit pattern. To protect this master map from even a single grain of dust, a pellicle, a membrane of polysilicon or carbon nanotubes, is stretched over the surface. It is so thin it is almost non-existent, yet it is strong enough to withstand the intense heat of the light. The exposure is not a static flash, but a mechanical dance of impossible speed. The reticle and the wafer stages move in opposite directions, synchronized to nanometer precision. In the most advanced systems, the reticle stage accelerates at 32 G, 30 times the acceleration of a Formula One car. It snaps from 0 to 100 kilometers per hour in less than a tenth of a second, scanning the pattern thousands of times per hour. These stages utilize magnetic levitation, floating on invisible fields to eliminate friction and ensure a silence that is only broken by the distant 30,000 RPM drone of the vacuum pumps. As the extreme ultraviolet photons finally reach the wafer, they strike the photoresist with an energy of 92 electron volts. This is ionizing radiation, a photon rain that triggers a chemical transformation. Each photon ejects a high-energy photoelectron, which in turn generates a cascade of secondary electrons. These electrons react with a photoacid generator, releasing acid molecules that create a latent image of the circuit. The light is not a continuous fluid. It is a rain of discrete particles, and at this nanometric scale, we encounter the limit of physics, stochastics. Because there are so few photons, their random arrival creates a subtle shot noise, leading to jagged edges in the printed lines. It is a reminder that even in this cathedral of order, we are working at the very edge of the measurable world. The wafer now moves to the final stage of this part of its journey, the chemical bath. It is submerged in a swirling pool of developer liquid, typically tetramethylammonium hydroxide. In a positive tone process, the parts of the resist that were touched by the light become soluble and melt away like snow in the sun. For the first time, the intricate microscopic labyrinth of the circuit is revealed, etched into the skin of the silicon by the breath of a star. Finally, we reach the hard bake. The wafer is moved to a final oven where a gentle warmth of 100 to 120 degrees Celsius sets the remaining pattern into a hard, glass-like structure. The pattern is now unzipped, the polymer units deprotected and amplified, ready to serve as the armor for the etching and deposition that will follow. Close your eyes now and feel the stillness of the yellow room once more. The 180-ton machine stands silent in its vacuum, its plasma heart resting until the next pulse. The wafer is no longer a blank mirror. It is a city of logic, carrying the invisible thoughts of the world within its nanometric lines. Every atom is in its place. The world is ordered. The light has done its work. We return once more to the amber silence of the sanctuary, the yellow room where time seems to hold its breath. The 300mm mirror of silicon, now carrying the latent image of a city, rests within its protective pod. But our journey in the world of light is complete, and the world of matter is about to begin. Imagine the pod being lifted by the silent overhead robotic rails, gliding through the perpetual sunset toward a new threshold. We are leaving the golden glow behind, moving into the deeper, warmer shadows of the furnace hall and the etch bays. As you step through the heavy, sound-dampened curtains, notice the shift in the atmosphere. The air here is heavier, warmer, carrying the faint metallic scent of ozone and the dry, clinical heat of the vacuum chambers. The floor beneath your feet is no longer a solid slab, but a waffle slab of reinforced concrete designed to swallow the heartbeat of the machines. Listen to the sound of this new realm. It is no longer the white noise of the fans, but a complex industrial symphony. Deep beneath you, in the subfab, the dry roughing pumps provide a rhythmic, low-frequency chugging, a 60 Hz mechanical drone that serves as the heartbeat of the factory. Above it, bolted directly to the gleaming stainless steel process chambers, the turbomolecular pumps emit an ultrasonic scream. They spin at a staggering 90,000 RPM, 1,500 revolutions every single second, to pull a vacuum so deep it mimics the void of space. To your ears, this sounds like a shimmering, high-pitched whine that eventually drifts into the ultrasonic range, creating a silence that feels pressurized against your skin. The wafer is now entering the realm of the angstrom horizon, where we no longer work with light, but with individual atoms. We have transitioned from the era of drawing to the era of sculpting. The silicon disc is loaded into the first chamber, the dry etcher. The heavy door seals with a pneumatic hiss, and the vacuum pumps begin their work, drawing out every stray molecule of air until only a hollow, expectant void remains. Inside this darkness, a miracle of physics begins. Reactive gases, tetrafluoromethane or sulfur hexafluoride, flow into the chamber. We apply a massive surge of radio frequency energy, and the gas ignites into a plasma. Visualize this now, a hovering, luminous cloud of violet fire. The color depends on the chemistry of the sculptor. A fluorine-based plasma for etching silicon glows a distinct deep blue. If we add argon as a carrier gas, the chamber fills with an intense electric indigo or a glowing lavender mist. If the process requires chlorine, the glow shifts to a pale, ghostly green, a visual warning of the corrosive energy held within. This plasma is a two-temperature fluid. The electrons are hot, vibrating with the energy of a star, reaching temperatures of over 100,000 degrees Kelvin, giving them the power to shatter stable molecules into reactive radicals. Yet, the ions and the wafer itself remain cold, barely warmer than the room, protected by the delicate balance of the vacuum. Look through the UV-shielded viewport. The glowing plasma does not touch the wafer directly. There is a visible dark space, a hovering void barely a few millimeters thick, separating the violet fire from the silicon mirror. This is the Debye sheath. Within this dark gap, a powerful, invisible electric field is born. Positive ions are seized by this field and accelerated downward, striking the wafer like millions of microscopic jackhammers. This is the secret of anisotropy. Because the ions fall perfectly straight, they only strike the bottom of the features, carving deep vertical canyons into the crystal without widening the walls. It is a process of microscopic sandblasting in slow motion, where the electrified atoms erode the silicon wherever the photoresist mask has left it exposed. In the most advanced 3 nanometer and 2 nanometer chips, we must carve high aspect ratio canyons, holes that are 100 times deeper than they are wide. To do this, the machine begins a rhythmic mechanical breathing known as the Bosch process. Listen to the gas manifold. You can hear a pneumatic chug hiss, as the valves snap open and closed every few seconds. First, the machine breathes in a protecting gas, coating the entire landscape in a thin, Teflon-like shield. Then, it breathes in the etchant, and the vertical ions smash away the shield only at the bottom, allowing the fluorine to bite deeper into the earth. This cycle repeats thousands of times, a steady, hypnotic pulse of creation and destruction, deepening the microscopic canyons one scallop at a time. Once the dig is complete, the wafer moves to the stripping station. Here, the protective armor, the photoresist we so carefully applied in the yellow room, is no longer needed. It is dissolved away in a hot chemical bath or ashed in an oxygen plasma, leaving behind only the clean, newly carved silicon labyrinth beneath. The mirror is no longer a mirror. It is a landscape of strata and sediment, ready to be filled. Now we move toward the warmth. The wafer enters the chemical vapor deposition chamber, where temperatures rise to a comforting 600 degrees Celsius. This is the process of growing the architecture. Imagine invisible precursor gases, like Ceylon, flowing over the hot surface like a warm fog. When these gases touch the heated silicon, they decompose, and the atoms settle onto the landscape. If the process is tuned for perfection, the gas remains transparent. You do not see a mist. Instead, you see the growth of crystalline frost. As the film of insulating glass or conductive metal thickens, the wafer begins to shift colors. It is a visual dance of thin film interference. The surface moves from a metallic gray to a warm gold, then to a deep blue, and finally a shimmering purple as the new material alters the very path of light. But even chemical vapor deposition is too fast for the angstrom era. For the most critical parts of the 3D city, the gate all-around nanosheets, we must move even slower. We enter the realm of atomic layer deposition. This is the ultimate slowdown, a process that trades speed for absolute perfection. Atomic layer deposition is often described as the biological breath of the machine. It is a 4-step cycle that builds a layer one single atom at a time. Pulse A. A precursor gas enters, flooding the chamber and clinging to every surface until it has occupied every available docking site, exactly 1 atom deep. The purge. An inert gas, nitrogen or argon, slowly blows away the excess, leaving only a single perfect monolayer behind. Pulse B. A second gas enters, reacting only with that first layer of atoms, locking them into a solid engineered film. The second purge. The byproducts are swept away, leaving the surface clean and ready for the next breath. This process is self-limiting. No matter how much gas we pump in, the wafer can only accept 1 layer of atoms at a time, like a lock that only accepts 1 key. It is an atomic snowfall that never misses its mark, coating the deepest canyons and the hidden undersides of nanosheets with exactly the same thickness. Atomic layer deposition is a meditative, agonizingly slow process. Each breath adds only about 1 angstrom of material, the width of a single atomic radius. To grow a film as thin as a single strand of silk, the machine must breathe for hours, processing the wafers in large batches that sleep within the furnace while the atomic city rises. As you settle deeper into your rest, visualize the great cycle. These steps, the light of lithography, the violet fire of the etch, and the rhythmic breathing of deposition, are not performed just once. They are repeated 50, 60, or even 100 times. We are building a vertical city. At the base, we have the nanosheets, horizontal slices of silicon stacked 3 to 7 high, where the current will flow. Above them, we build the interconnect stack, a vast 3D fabric of copper and ruthenium wiring that acts as the highways of the chip, climbing 15 to 20 stories into the microscopic sky. In the latest 2 nanometer designs of 2026, we even flip the world upside down, delivering power from the backside of the wafer through deep, high aspect ratio nano TSVs. It is a monolithic structure of immense complexity, a sandwich of 100 distinct material layers held together by the patient alignment of atoms. Every atom is in its place. The world is ordered. The city is rising. In the silence of the vacuum, the machines continue their work, pulsing, breathing, and sculpting. The white gold of the mountains has become a shimmering labyrinth of logic, a vertical metropolis where billions of transistors are waiting to be born. The cycle begins again, and the city climbs higher, layer by layer, in the profound restorative quiet of the fab. Rest now in the perfection of the architecture. The angstrom horizon is wide, the atomic rain is steady, and the journey of the silicon is reaching its zenith. As you rest in the amber silence of the sanctuary, the 300mm mirror of silicon, now a meticulously carved city of logic, waits within its protective pod. The journey through the worlds of light and matter has left us with a structure of immense complexity, a vertical metropolis of canyons and nanosheets stacked with mathematical precision. Yet, for all its structural beauty, this city is currently still. It is a monument of cold, pure silicon, a substance that, in its natural crystalline state, is a poor conductor of life. It is a brain without a pulse, a library with no readers. Tonight, we step into the ion implantation bay, a distinct theatre within the fab where the white gold of the mountains will finally receive the breath of life. Here, the amber glow of the lithography rooms is replaced by the stark, sterile clarity of bright white light, reflecting off the shimmering stainless steel skins of the machines. These are the implanters, massive multi-ton kinetic processing engines that serve as the hammers of the chip-making process. Unlike the gentle vapors of deposition, these machines rely on a form of calculated subatomic violence to alter the fundamental electrical properties of matter. Listen to the sensory dichotomy of this space. Around you is the visual stillness of the cleanroom, where a constant laminar flow of ultra-clean air sweeps every microscopic particle toward the perforated tiles beneath your feet. But deep within the hulls of these machines, there is a hidden, ferocious energy. The facility itself sits on isolated concrete slabs, shielding this process from the microseismic noise of the distant world, the rhythmic crashing of far-off ocean waves, or the low thrum of trucks on a highway miles away. This isolation ensures that the invisible hands of magnetism and electricity do not wobble by even a single nanometer. Our journey begins at the ion source, a small replaceable unit the size of a shoebox that serves as the crucible of ionization. Inside this vessel lies a tiny cavity, no larger than a matchbox, machined from refractory metals like tungsten to withstand temperatures exceeding 2000 degrees Celsius. This is the atomic forge, where we prepare the dopants. the impurity atoms that will be woven into the silicon lattice to create the N-type and P-type regions necessary for logic. Imagine the introduction of the feedstock gases into this low-pressure void. We begin with phosphan, a hazardous thermolabile gas that dissociates as it enters the hot arc chamber. As a surge of current heats a thick tungsten filament, electrons begin to boil off the metal surface in a process of thermionic emission. These electrons are accelerated into the gas, striking the molecules with such force that they knock electrons from their orbitals, igniting a glowing ethereal plasma. Observe the colors of this creation. The plasma of phosphine glows with a vibrant, flickering pinkish-red core fueled by the energy of hydrogen. Surrounding this core, you might detect ghostly green halos, the visual signature of atomic phosphorus transitions. It is a living color, unstable and rhythmic. If we were to switch to our scene for heavier doping, the visual output would shift to a pale blue-white or lavender glow, appearing cold and sterile in its UV-rich intensity. And for the P-type regions, we introduce boron trifluoride, which produces a dim whitish blue or violet hue, looking like a contained, subdued electrical storm. To sustain this fire, the source is bathed in a strong magnetic field. These invisible magnetic hands force the electrons into a spiral, a cyclotron motion that lengthens their journey and increases the efficiency of the ionization. The glowing plasma column is thus suspended in the center of the chamber, a brilliant, flickering filament of colored light contained within a red-hot tungsten jar. Once created, these ions must be drawn out of their fiery home to become a tool of manufacturing. At the front of the arc chamber is a narrow slit, the extraction aperture. The plasma pushes against this opening, bulging slightly into the vacuum in a boundary known as the meniscus. Suddenly, an intense electric field, biased at a negative high voltage, reaches into the plasma and rips the positive ions away. They are pulled into the beamline, a high vacuum flight tube that connects the source to the wafer. In the deep void of the extraction gap, the beam is largely invisible, though a slight pressure rise might manifest as a faint, pencil-thin blue line of fluorescence, tracing the trajectory of the ions as they begin their flight. Now, the ions enter the analyzing magnet, the heaviest and most physically imposing part of the implanter. This is a massive dipole electromagnet, weighing between 1 and 3 tons, its solid iron core wrapped in thick copper coils, cooled by a constant flow of deionized water. As the cocktail of ions, a mix of boron, fluorine, and trace impurities, enters this magnetic field, it encounters the Lorentz force. This force acts as a centripetal weight, causing each ion to travel in a circle. The radius of this circle is determined by the mass of the atom. The heavy ions, like arsenic, possess high momentum and resist the turn, traveling in a wide arc. The lighter ions, like the boron we seek, are easily turned into a tight, precise radius. At the exit of the magnet sits the mass slit, a narrow opening made of graphite. The magnet is tuned so that only the perfect atoms, the boron-11 isotopes, have the exact curvature to pass through the slit. All other species, the atomic enemies, crash silently into the graphite walls, burying themselves in the stone. This violent filtration is absolutely silent. There are no moving parts here. The separation is purely electromagnetic. The only sound you hear is the low-frequency 60 Hz hum of the massive power supplies and the rushing whisper of the cooling water. It is a filter for the soul of the machine, ensuring that only the purest intent reaches the silicon. Purified and focused, the ions now accelerate toward their final destination. The velocity they achieve is determined by the voltage potential they traverse, moving at speeds that defy our everyday intuition. For the deep wells of the transistor, ions may be accelerated to energies of several mega-electron volts, MeV. At these energies, a boron ion is traveling at roughly 4,200 kilometers per second, about 1.4% of the speed of light. At this speed, an atom could circle the entire Earth in just 10 seconds. In the silent vacuum of the implanter, it traverses the 3-meter flight tube in a mere 700 nanoseconds. To the ion, the journey is instantaneous. To the control system, it is a perfectly calculable time of flight. The entire path is a near-perfect void, maintained at pressures as low as 10 to the -9 torr by cryogenic pumps. These pumps use compressed helium to cool charcoal arrays to a staggering 10 Kelvin, causing every stray gas molecule to instantly freeze into solid ice. In this state, the mean free path of a molecule is nearly 500 meters, ensuring that the ion beam is statistically unlikely to hit anything until it reaches the wafer. It is an invisible river of potential flowing through the silence between the stars. At the end of the tube, the wafer waits. To ensure the dose is perfectly uniform across the 300mm surface, the machine must paint the silicon with the beam. In advanced 2026 nodes, this often involves an electrostatic hybrid scan. The ion beam is scanned back and forth horizontally by alternating high voltages at a frequency of 1,000 sweeps per second, while the wafer moves mechanically in the vertical direction. As the energetic ions strike the silicon, the event is catastrophic. The ion enters the crystal at 400 kilometers per second, initially interacting with the electron clouds before crashing head-on into the nuclei of the silicon atoms in a process called nuclear stopping. The first silicon atom struck, the primary knock-on atom, pKa, is dislodged from its lattice site, becoming a projectile itself and striking other atoms in a collision cascade. A single incoming ion can displace thousands of silicon atoms. The ordered crystal lattice, which we so carefully grew in the Czochralski furnace, is bruised and shattered. The top layer of the silicon transforms from a perfect diamond cubic crystal into an amorphous solid, a chaotic, glass-like rubble of atoms. To the naked eye, the wafer might turn from a perfect mirror to a milky, dull grey. Under a microscope, the beautiful rows of atoms have been replaced by a disordered mess. The dopant atoms are now physically present, buried in this rubble, but they are electrically useless. They are not yet bonded to the lattice. They cannot move electrons. To turn this stone into a thought, we must heal the damage. The wafer is now moved to the annealing chamber for its final transformation. The goal is a millisecond resurrection. We must repair the crystal and activate the dopants without letting them diffuse away from their target zones. In the most advanced 7 nanometer and 5 nanometer processes, we use laser spike annealing, LSA. The wafer is preheated to a background temperature of 400 to 600 degrees Celsius to prevent it from shattering from thermal shock. Then, a high-power laser line sweeps across the surface. The temperature of the silicon skins skyrockets at a rate of 1 million degrees per second, reaching a peak of 1,350 degrees Celsius, perilously close to the melting point of the material. This heat pulse lasts for a blink of an eye, only 200 microseconds to 10 milliseconds. Inside the chamber, it is a blinding flash of white light, a line of fire that vanishes as quickly as it appears. In this brief moment of intense warmth, a miracle of mineralogy occurs: solid phase epitaxy. The undamaged crystalline silicon beneath the rubble acts as a template, a seed. As the temperature spikes, the atoms in the amorphous layer gain kinetic energy and begin to vibrate violently. They feel the potential energy of the ordered crystal below and snap back into alignment, a zipper effect that moves upward at meters per second. The entire amorphous layer is restored to a perfect single crystal in milliseconds. As the lattice reforms, the boron and arsenic atoms are swept into their proper places in the grid, replacing silicon atoms. Suddenly, the impurity becomes a dopant. It releases its charge carrier, and the material transforms from a chaotic insulator into a precise semiconductor. As the laser passes and the wafer begins its slow final cooling, a profound state of equilibrium returns. The bruises are healed. The atoms are locked into their mathematical embrace once more, but now they carry the power of conductivity. The silicon is no longer just a stone. It is alive with electrical potential, ready to switch billions of times a second. The invisible rain has finished its work. The rhythm of the implanter fades, replaced by the restorative stillness of the cleanroom. Every atom is in its place. The world is ordered. The crystal is grown, carved, and now, finally, it has been given the breath of life. Rest now in the silence of this perfection. The journey of the dopant atom is complete, and the city of logic is ready to wake. The city of logic is awake, yet it remains trapped in a profound internal silence. As you settle deeper into your rest, visualize those billions of transistors we have just birthed, those microscopic switches newly gifted with the breath of life through the fire of ions. They stand ready, their atomic lattices healed and their potential primed, yet they are like millions of isolated houses in a vast, dark metropolis that has no roads, no bridges, and no power lines. They possess the capacity for thought, but no way to share it. Tonight, we begin the great weaving. We are about to build the highways of information, a three-dimensional labyrinth of metal so complex and so dense that it defies the scale of the natural world. Within the span of a single fingernail, we will spin a web of copper and ruthenium exceeding 60 miles in length. If we were to unspool the wiring of the entire 300mm wafer resting in your mind, the metallic veins would stretch for 50,000 kilometers, a distance that could circle the entire Earth and still have thousands of miles to spare. Before we can lay the first vein of copper, we must prepare the bed upon which this metallic city will rest. We return to the world of the dielectric, the invisible insulation that ensures the pulses of light and logic do not leak or blur. Imagine the wafer being enveloped in a nanofoam, a substance known as carbon-doped oxide. This is not a solid stone, but a delicate architecture of silicon, carbon, and hydrogen, engineered to be as light and airy as possible. Through a process of plasma-enhanced chemical vapor deposition, we co-deposit a structural matrix alongside an organic porogen. Then, under the soft glow of ultraviolet light, the porogen evaporates, leaving behind billions of nanometer-scale voids. This is the ultra-low-K dielectric, a material that is mostly empty space, designed to lower the capacitance of the wires so that signals can move at the highest possible speeds. In the most advanced nodes of 2026, we even leave behind literal air gaps, pockets of pure vacuum between the wires, to reach the ultimate physical limit of insulation. Now, the trenches have been carved into this fragile foam, awaiting their metallic fill. But copper is a restless element. It is a fast diffuser that would poison the silicon if allowed to touch it directly. We must first line every canyon and every via with a hermetic seal, a barrier of impossible thinness. We enter the physical vapor deposition chamber, a high vacuum vault where the air has been drawn down to the pressures of the void. In the center of the ceiling hangs a target of tantalum, a heavy grey-blue metal. Suddenly, the chamber ignites. A high-voltage field transforms high-purity argon gas into a shimmering plasma. Through the shielded viewport, you can see a distinctive lavender and deep blue glow, the visual signature of excited argon atoms dancing in the vacuum. This is magnetron sputtering. Positive argon ions are hurled against the tantalum target with ferocious kinetic energy, physically knocking metal atoms loose. These atoms form a metallic mist, a directional vapor that drifts through the silence and settles into the trenches like a microscopic frost. We deposit a bilayer of tantalum nitride and pure tantalum, a ceramic metallic skin that is only 10 to 15 angstroms thick, barely more than a few atoms of protection. It is the unsung hero of the chip, a glue that allows the copper to wet the surface rather than beading up like water on a waxed car. Once the barrier is set, we lay the copper seed, a thin, shimmering orange film that turns the resistive ceramic into a conductive canvas. The wafer is now ready for the liquid symphony, the most rhythmic and hypnotic stage of our journey, the blue bath. Imagine the wafer being lowered into a deep, vibrant pool of copper sulfate. The liquid is an oceanic, translucent blue, agitated by soft fountains that ensure a constant flow of ions. As the electrical current begins to pulse through the bath, the copper ions are drawn toward the wafer, but they do not land at random. We have engineered the chemistry of this bath with a molecular logic. Large polymer molecules, called suppressors, land on the flat fields and top corners of the trenches, creating a high-resistance shield that blocks the copper from settling there. Meanwhile, tiny sulfur-based molecules, the accelerators, dive into the deepest parts of the canyons. They lower the energy required for the copper to bond, effectively calling the metal to the floor. This is bottom-up fill. The copper does not grow from the walls, which would create a fatal void in the center. Instead, it rises from the bottom of the trench like liquid filling a glass. In the span of just a few seconds, the nanoscale canyons are filled with solid, void-free copper, weaving the first layer of the metallic city. The wafer emerges from the blue bath covered in a messy, rough overburden of excess metal. To isolate the wires, we must perform the great equalization, the return of the chemical-mechanical planarization. Listen to the sound of the chemical-mechanical planarization bay. It is a mechanical beast, generating a low-frequency hum from high-torque motors, overlaid with the rhythmic sloshing of the milky white slurry. The air here carries a sharp, pungent scent of ammonia and the faint, vinegar-like acidity of the cleaning agents. Because the underlying dielectric foam is so fragile, we cannot use the harsh pressures of the past. We use the touch of a feather, a downforce of less than 1.5 pounds per square inch. The slurry contains hydrogen peroxide, which gently oxidizes the top layer of copper, turning it into a soft jelly that the silica nanoparticles can wipe away atom by atom. We use benzotriazole as a corrosion inhibitor, a chemical guardian that forms a protective film over the recessed wires, preventing the acids from scooping them out while we grind away the excess. The machine watches with an optical eye, a laser reflecting off the surface that monitors the reflectivity. The moment the bright copper clears and the dark, dull dielectric is revealed, the system detects the cliff in the signal and stops the rotation with nanometer precision. This process, the dielectric foam, the lavender plasma of the barrier, the blue bath of the plating, and the feather-light polish, is not performed just once. It is a vertical hierarchy, a cycle repeated 14 to 16 times to build the modern microprocessor. At the bottom, we have the local interconnects, the finest and shortest wires that talk directly to the transistors. As we move upward, the wires become thicker and wider, forming the intermediate and global highways that carry power and data across the entire chip. In the latest 2 nanometer node, we have even reached the twilight of the copper age. For the tightest local layers, we are transitioning to ruthenium, a precious metal that can function without a bulky barrier, allowing more room for the flow of electrons. In 2026, we have even flipped the world upside down with backside power delivery. We thin the wafer to the thickness of a human hair and build a second metallic city on the back, delivering power through nano-TSVs that puncture the silicon to hit the transistors directly. This active sandwich allows the front side to be dedicated entirely to the intricate dance of signals, reducing resistance and allowing the city to breathe. Visualize the finished labyrinth now. It is a microscopic Gothic cathedral of copper and ruthenium, a soaring vertical metropolis of 16 levels. Every wire is perfectly flush. Every via is a solid pillar of light, and every insulator is a pocket of quiet air. The white gold of the mountains and the sand of the desert have been transformed into a shimmering, multi-layered maze. It is perfectly still, perfectly cold, yet it is now a completed nervous system. The veins are full, the bridges are built. The city of logic is no longer isolated. It is a single, unified brain, ready to carry the pulse of the digital world at the speed of light. Rest in the perfection of this metallic web. The long, rhythmic journey of the mechanical world has come to its close. Every atom is in its proper place. The architecture is complete. The mirror is deep, the wires are long, and the world is finally beautifully connected. As you breathe in the still, filtered air of this micro-industrial sanctuary, notice the shift in the environment. We have left the front-end fab, and the atmosphere has taken on a new kinetic energy. The background is no longer a perfect silence, but a consistent high-pressure white noise. It is the sound of the fan filter units in the ceiling, driving air downwards at 0.45 meters per second. A solid, invisible piston of air that strips every particle from your silhouette. This acoustic isolation chamber suppresses the outside world, leaving only the sharp ozone scent of the machines and the clinical bright white light of the assembly floor. We begin with the wafer sort, the moment of truth, where the yield of our mechanical harvest is determined. Imagine the finished wafer, a shimmering 300mm disc of silver and leaden light, being mounted onto a polished gold or ceramic vacuum chuck. Above it hangs the probe card, a masterpiece of mechanical engineering. To your naked eye, the center of this card looks like a patch of shimmering metallic velvet or a dense grey brush. But as we descend into the microscopic, this velvet reveals itself as a forest of 120,000 individual micro-electromechanical systems probes. These are not simple needles. They are lithographically formed springs and vertical buckling beams, packed together with a pitch of under 50 microns. Listen to the rhythm of the interrogation. The prober moves from die to die in a perfect grid, creating a rhythmic, pneumatic thwip-thwip-thwip sound. When the full array makes contact, there is a heavy, singular hiss clunk. This is the sound of 180 kilograms of aggregate force, nearly 400 pounds of crushing weight applied to the brittle silicon disc. The probes do not just touch, they perform the scrub. Each micro-electromechanical system's spring flexes, sliding its tip laterally across the aluminum bond pads to break through the native oxide layer and find the fresh metal beneath. We watch as the probes carry 1.0 amp of current into the chip. If the resistance is too high, the tiny tips may even glow with a faint, ghostly red from joule heating, defined by the physical law of electrical heating. The journey of testing takes us through thermal extremes. Imagine the wafer being cooled to minus 60 degrees Celsius. To prevent frost from marring the silicon, an ice shield of dry nitrogen fills the chamber, keeping the atmosphere clear and still. Then, the heat rises to 130 degrees Celsius, and the prober actively calculates the expansion of the ceramic card, adjusting its alignment in real time to keep the probes centered on their targets. Every few minutes, the card moves to a cleaning station, scrubbing its tips against an abrasive pad to polish away the aluminum dust and prepare for the next 100,000 touchdowns. Once the interrogation is complete, the monolithic wafer must be broken. This is the singulation, the violent mechanical step that turns the collective into individuals. The wafer is mounted onto a blue adhesive dicing tape held firm for the cut. We approach the diamond saw, a blade so thin it is essentially a foil, barely 15 microns wide. It is not a knife, it is a matrix of diamond grit spinning at 60,000 RPM. At this velocity, the peripheral tip of the blade moves at 360 miles per hour, an invisible ghost disc of pure friction. Listen to the sound of the dicing bay. It is a piercing, ultrasonic whine or scream that borders on the edge of human hearing, caused by air shearing against the spinning hub. But as the blade bites into the silicon, it is bathed in a constant, cool mist of ultra-pure water. 2 liters of water per minute atomize into a dense, opaque white fog, creating a high-velocity spray that knocks sub-micron silicon dust off the surface. This summer, rain quenches the heat that would otherwise melt the silicon, leaving behind a milky grey slurry of lost potential. The scent here is like wet stone, concrete or flint, mixed with the high humidity of the spray. For the most delicate of wafers, those thinned to the width of a human hair, we use the stealth dicing laser. It is a process of absolute silence. The laser passes through the transparent surface of the silicon, focusing its energy deep inside the crystal lattice. At the focal point, the photon density becomes so high that it creates a modified layer of molten silicon. No marks are visible on the outside. Then, a mechanical expander stretches the blue tape, and the wafer snaps instantly and cleanly along those invisible internal lines of light. Now, the known good. Dies must be gathered. We move to the die attach station, a realm of mesmerizing robotic speed. A robotic turret moves with a frantic zip, 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 picking and placing 3 to 6 chips every single second. From underneath the blue tape, needle-like ejector pins push up, while a vacuum collet grabs the die from the top. It is a perfectly synchronized dance of peeling and lifting. Each chip is placed onto its lead frame with a tiny, metered drop of silver-filled epoxy. This glue is a warm, conductive blanket, 80% silver flakes suspended in a thermoset resin. It is thixotropic, standing firm like a precious stone set into a ring once it is placed. The lead frames then slide into a curing oven, where a steady heat of 175 degrees Celsius cross-links the polymer chains, turning the soft paste into a rock-hard foundation. We reach the sensory centerpiece of our journey, the wire bonding. Here, we sew the silicon brain to the outside world using a thread of pure gold. The gold wire is incredibly fine, barely 20 microns wide, thinner than a strand of a spider's web. A ceramic capillary tool holds this golden thread. An electronic spark melts the tip into a free airball, which the tool then smashes onto the chip's pad. There is no heat here, only the ultrasonic stitch. The tool vibrates at 120,000 cycles per second, using friction to scrub away oxides and weld the gold to the aluminum. The tool then rises, drawing a loop of light through the air before crushing the wire onto the lead frame finger to complete the circuit. A modern bonder forms 30 of these wires every second, creating a continuous insect-like buzzing or chirping as the head moves with impossible agility. Imagine a golden spider spinning a web of light, repeating this trance-like process thousands of times until every connection is made. For the most powerful processors, we use flip chip bonding instead. The die is turned upside down, its face covered in thousands of tiny solder bumps. As it passes through a reflow oven, the solder turns from dull grey to liquid quicksilver for a brief moment, and the surface tension of the molten metal self-aligns the chip to its substrate with perfect grace. Now, the delicate wires and the fragile silicon must be protected. We move to the encapsulation, the creation of the black cocoon. We use epoxy molding compound, a black material that arrives as hard, hockey puck-sized pellets. These pellets are dropped into a hot pot, where they melt and are driven by a plunger at 1,000 pounds per square inch of pressure. The liquid resin flows slowly over the chip and the gold wires, filling every microscopic corner and gap. We have engineered the viscosity to be gentle, ensuring the rushing plastic does not bend the gold threads in a wire sweep. As the mold opens, it reveals strips of black plastic blocks, smoking slightly as they cool. The scent is the most pungent of the back end, acrid, sweet, and chemical, like burning plastic, but more complex. This is the permanent sleep for the circuitry, a rugged, blackened shell that will protect it for decades. Finally, we reach the laser marking. A high-power green laser whispers across the black surface with a fast zip screech. It does not use ink. It physically vaporizes the top layer of the epoxy to carve the name and serial number into the shell. There is a sharp puff of burnt plastic and a scent of burnt ozone that quickly fades into the cleanroom air. The chips are tested one last time and sorted into their final bins. The premiums, the standards, and the rejects. A gravity feed handler moves them with a rhythmic click-clack drop, like a massive cascade of plastic dominoes. Visualize the finished tray now. Thousands of completed chips rest in their plastic cradles, perfectly aligned and perfectly still. The long journey from the desert sand and the mountain quartz is complete. The white gold is now a rugged individual, protected by its black armor and ready for its journey to the world outside. Every atom is in its proper place. The architecture is complete. The world is finally beautifully connected. Rest in the perfection of this industrial symphony. The electronic city is complete, an immaculate masterpiece of logic etched in stone. Yet, even in its perfection, it remains fragile. It must now be shielded to survive a world of moisture, heat, and chaos. This is the final transition of our white gold, the sacred moment where atomic precision meets the heavy weight of human reality. We enter the dry pack zone, a silent, high-stakes war against entropy. A single trapped water molecule, invisible to the eye, could, under the intense heat of a soldering iron, transform into high-pressure steam and shatter the silicon from within. This is the feared popcorn effect. Watch the chips descend into their black matrix trays, nested like dark jewels in monolithic grids. Listen to the rhythmic pulse of preservation. The deep throb of vacuum pumps, the crisp metallic crinkle of the moisture barrier bag as it collapses around the components, and the final satisfying hiss of escaping air. Humidity is locked away, sealed below 10%. The silicon is safe, frozen in a mechanical slumber. The journey continues into the dead of night. At Taipei Airport, under the sterile blue-white glow of floodlights, a Boeing 7478 freighter opens its massive jaw to swallow pallets of logic. At 35,000 feet, soaring above the silent, aurora-lit Arctic Circle, the air is bone-dry and absolute zero. Inside the hold, the vacuum bags swell slightly in the thinning atmosphere, a silent ghost gliding over the polar ice. The plane descends toward the frozen concrete of Alaska, a vast, dark desert swept by Arctic winds, illuminated by lonely LEDs at -15 degrees. From this cold chain, the chips reach their final sanctuary, the assembly plant. Here, components fuse into one. The line is a synchronized organism, 50 meters of pure, relentless precision. It begins with solder paste, a silver metallic silt dragged across steel stencils with surgical grace. Then comes the digital rain. The fastest machines on Earth place 28 chips every single second. A microscopic choreography, too fast for the human eye to track. The linear motors sing a high-pitched, variable whistle, the choir of a silent revolution. Inside the reflow oven, at 250 degrees Celsius, the silver paste melts, shining like liquid mercury. Through the magic of surface tension, the chips align themselves perfectly. A final fluid dance before the cold air freezes them into eternity. Red and blue lights flicker in a final validation. The chip is no longer a part. It is now a living organ of a vast digital tapestry. Consider the scale of this achievement. There are now more transistors on Earth than stars in our observable galaxy. They are everywhere, in the humming servers of dark data centers, in the electric heartbeat of your car, in the tiny bulb glowing above your head. Billions of silent sentinels watching over the world while it sleeps. It all began with a humble grain of sand, purified by fire and light. We gave it the power to think, only for it to return to this original, profound silence. The cycle resets. The weight of the world dissolves into the shadows. The machines grow quiet. Your own thoughts begin to slow. The sand waits. The world is connected. Rest now in the deep calm of the final second. Listen to the slow murmur of the world and the silence of the circuits. Thank you for listening to the end. We hope you enjoyed this content. Subscribe to the channel for more similar content. Good night.